Welcome, students. Think of the atmosphere as a protective blanket surrounding our Earth. This invisible layer makes life possible and protects our planet every moment.
How to understand this chapter better. This chapter explains how the atmosphere, weather, climate, seasons, monsoon, and climate change are connected. To understand it clearly, think of the atmosphere as a protective blanket around the Earth. It gives us the air we breathe, protects us from harmful rays of the sun, keeps the Earth warm enough for life, and creates the conditions for rain, wind, clouds, and storms.
Section 1. Introduction and Big Questions. Chapter Overview. Atmosphere and Climate. This chapter studies the thin envelope of air that surrounds the Earth and everything it makes possible: the air we breathe, the clouds, the rain, the winds, and the seasons. You will move step by step, first understanding what the atmosphere is and what it is made of, then how it is arranged in layers, then how it produces weather and climate, and finally how human activity is now changing that climate. Keep one big idea in mind throughout. The atmosphere is a single connected system, so a change in one part, like temperature, affects everything else, like pressure, wind, and rain. Big Question 1. Composition of the atmosphere. The first guiding question is, what is the air actually made of? Most people assume air is just oxygen, but oxygen is only about a fifth of it. Asking this question prepares you to discover that nitrogen is the largest part, that carbon dioxide is tiny but powerful, and that invisible water vapor and dust play a huge role in rain and clouds. Hold this question in mind as you read Section 2. 3. Big Question 2. Layers of the atmosphere. The second guiding question is, how do the different layers of the atmosphere affect life on Earth? The atmosphere is not uniform. It is stacked in layers with very different temperatures and jobs. One layer holds our weather, another shields us from ultraviolet rays, another burns up meteors, and another reflects radio signals. Keep asking how each layer protects or serves us. 4. Big Question 3. Mechanism of monsoon. The third guiding question is, how does the monsoon actually work? The monsoon is the yearly rhythm of winds that brings India most of its rain. The key idea to look for is that land and sea heat and cool at different speeds, and this difference reverses the wind direction between summer and winter. This question sits at the heart of Indian agriculture and daily life. 5. Big Question 4. Reducing carbon footprint. The fourth guiding question is, how can we reduce our carbon footprint? A carbon footprint is the total greenhouse gases our daily choices release. This question turns the chapter from knowledge into action, asking you to look at your own transport, electricity, water, and waste habits, and find ways to lower your impact on the climate. 6. What is the atmosphere? The atmosphere is the blanket of air that completely surrounds the Earth. It is a mixture of gases, water vapor, and dust held close to the planet. This blanket is invisible, but it is essential. It supplies the gases living things need, shields the surface from harmful radiation, and keeps temperatures within a range that supports life. Without it, Earth would be a lifeless, airless rock like the Moon. 7. Atmosphere held down by gravity. The atmosphere does not drift away into space because Earth's gravity constantly pulls it downward and holds it in place. This is why the air is densest near the ground, where gravity's pull packs the molecules closely, and thinner higher up. If Earth's gravity were much weaker, the gases would slowly leak away, which is exactly why small bodies like the Moon cannot keep an atmosphere. 8. Understanding gravity. Concept box. Gravity is the force of attraction that exists between any two objects that have mass. The greater the mass of an object, the stronger its gravitational pull. Earth has enormous mass, so it pulls everything, including the molecules of air, towards its center. This same force keeps our feet on the ground, makes objects fall, and traps the atmosphere around the planet. 9. Functions of the atmosphere. The atmosphere performs two protective jobs that are easy to remember. First, it acts like a shield, filtering out much of the sun's harmful ultraviolet radiation before it reaches the surface. Second, it acts like a thermostat, trapping part of the sun's heat so the Earth stays warm at night and does not freeze, while also preventing the daytime from becoming unbearably hot. Together, these make the surface livable. 10. Atmosphere in weather and climate plus discussion. The atmosphere is the stage on which all weather and climate happen. Clouds, rain, wind, and storms all form within it. For discussion, imagine, what if there were no atmosphere? There would be no air to breathe, no sound needs air to travel, no weather, no protection from radiation or meteors, and wild temperature swings between day and night. This thought experiment shows just how much we depend on this thin layer of air. Section 2. Composition of the atmosphere. Introduction to composition of the atmosphere. The air is not a single substance, but a mixture of many gases blended together, along with water vapor and fine dust. These ingredients are mixed in fixed proportions near the surface, which is why air behaves in predictable ways everywhere on Earth. Understanding this mixture explains why we can breathe, why plants grow, and why the sky can hold clouds and rain. Nitrogen, the most abundant gas. Nitrogen makes up about 78% of the air, making it the single largest component by far. Although we breathe it in and out without using most of it, nitrogen is vital to life because plants need nitrogen compounds to grow, and these eventually pass into animals through food. Nitrogen also dilutes oxygen so that burning and breathing happen at a safe, controlled rate rather than violently. 13. Oxygen, essential for life. Oxygen makes up about 21% of the air and is the gas that humans, animals, and most living organisms need to survive. During breathing, our bodies use oxygen to release energy from food. Oxygen is also required for burning, combustion, which is why a fire cannot keep going without a supply of fresh air. 14. Trace gases, carbon dioxide and argon. Beyond nitrogen and oxygen, the air contains small amounts of other gases. Argon, about 0.93%, is an inert gas used in light bulbs and welding. Carbon dioxide, about 0.04%, is tiny in quantity but hugely important. Plants use it for photosynthesis, and it traps heat to keep Earth warm. Because it traps heat, rising carbon dioxide is a major cause of global warming. 15. Trace gases. Helium, neon, krypton, xenon. The atmosphere also contains extremely small quantities of rare gases, such as helium, neon, krypton, and xenon. These are called noble or inert gases because they rarely react with other substances. Despite their tiny amounts, they have practical uses: neon in glowing signs, helium in balloons, and others in special lamps. 16. Trace gases, ozone and hydrogen. Ozone and hydrogen are present in very small amounts. Ozone is a special form of oxygen that collects in the stratosphere, where it forms a shield against the sun's ultraviolet rays. Hydrogen is the lightest gas of all, so it is found mainly in the highest reaches of the atmosphere. 17. Water vapor in the atmosphere. Water vapor is water in gas form, and it ranges from about 0.1% to 0.4% of the air. Its amount varies greatly from place to place and time to time. Humid coastal air holds a lot, while dry desert air holds very little. Even in small amounts, water vapor is the source of all clouds, rain, and snow. 18. Role of water vapor. Water vapor is essential because it is the raw material for precipitation. When moist air cools, the vapor condenses into tiny droplets that form clouds, and when these droplets grow large enough, they fall as rain, snow, or hail. Water vapor also helps trap heat, adding to the atmosphere's warming effect. 19. Dust particles. The atmosphere carries countless tiny dust particles from soil, smoke, volcanic ash, sea salt, and pollen. Though they seem insignificant, they play a crucial role. Water vapor condenses around them to form cloud droplets. Without these particles to cling to, clouds and rain would form far less easily. 20. Composition varies with altitude. The familiar mix of gases stays fairly constant only in the lower atmosphere. As we go higher, the proportions change. Heavier gases thin out, water vapor and dust almost disappear, and very light gases like hydrogen and helium become relatively more common at the top. Overall, the air simply becomes thinner with height. 21. Reading the composition pie chart. A pie chart of air shows the composition at a glance. Nitrogen fills about 78% of the circle, oxygen about 21%, argon about 0.93%, carbon dioxide about 0.04%, and all other gases the remaining sliver. Reading it teaches an important lesson. The gases that matter most for life and climate, oxygen and carbon dioxide, are not the largest slices. Practice converting these percentages into a mental picture of how little carbon dioxide there really is. 22. Recall: nitrogen's usefulness for plants. Recalling grade 8 science, plants cannot use nitrogen gas directly from the air. Instead, bacteria and natural processes convert nitrogen into compounds, like nitrates, that plants absorb through the soil to build proteins and grow. Animals then get their nitrogen by eating plants. This is the nitrogen cycle, and it shows why the most abundant gas in the air is quietly essential to all food. Section 3. Structure of the atmosphere. Layered structure of the atmosphere. The atmosphere is not one uniform block of air. It is arranged in a series of layers, one above the other. Each layer has its own characteristics and its own role in supporting life and shaping weather. Picturing these layers as floors of a very tall building helps you keep track of what happens at each level. Basis of the layers. Scientists divide the atmosphere into layers, mainly on the basis of how temperature and density change with height. In some layers, temperature falls as you go up, while in others it rises, and these reversals mark the boundaries between layers. Density, how tightly packed the air is, also steadily decreases with altitude. Density decreases with altitude. Air is densest close to the Earth's surface because gravity pulls the molecules downward and the weight of the air above presses them together. As you climb higher, there is less air pressing down, so the molecules spread out and the air becomes thinner. This is why mountaineers at great heights find it hard to breathe. Understanding altitude. Altitude means the height of a place above mean sea level. Sea level is taken as the standard zero mark, and heights are measured upward from it. Altitude matters in this chapter because temperature, pressure, and density all change as altitude increases. Reading the layers diagram. A labeled diagram of the atmosphere stacks the layers from the surface upward: troposphere, stratosphere, mesosphere, thermosphere, and exosphere, with boundary zones, pauses, in between. Reading it, note the approximate height of each layer and one key feature of each. This visual overview makes the detailed descriptions that follow easier to remember. Troposphere. Introduction and height. The troposphere is the lowest layer, stretching to about 12 kilometers above the surface, higher over the equator, lower over the poles. It is the layer we live in, and the most important for daily life. Almost all the air's mass and nearly all its water vapor are found here. Troposphere. Temperature behavior. In the troposphere, temperature decreases steadily as altitude increases, roughly 6.5 degrees Celsius for every kilometer you rise. This is because the ground is warmed by the sun and then heats the air just above it, so air far from the surface stays cold. This cooling with height is why mountain peaks are snow-capped, even in warm regions. Troposphere: air, water vapor, and clouds. The troposphere contains the air we breathe and holds almost all the atmosphere's water vapor and dust. Because the ingredients for clouds, moisture and dust particles, are concentrated here, this is where clouds form. It is, in effect, the living and breathing layer of the atmosphere. Troposphere: weather phenomena. Nearly all weather happens in the troposphere. Rainfall, fog, mist, hail, thunderstorms, and winds all occur here. This is because the layer contains the moisture, dust, and temperature differences needed to drive weather. When we talk about the weather, we are almost always talking about events in this bottom layer. Tropopause: transition zone. The tropopause is the thin boundary zone that separates the troposphere from the stratosphere above. In this zone, temperature stops falling and stays roughly steady. It acts like a lid that limits how high most clouds and weather can reach. Stratosphere: introduction and extent. Above the tropopause lies the stratosphere, extending from about 12 kilometers up to around 50 kilometers. Unlike the troposphere, it is calm and stable with very little water vapor or dust. This calmness makes it very different from the busy weather layer below. Stratosphere: ideal for aeroplanes. Because the stratosphere is largely cloud-free and free from the weather disturbances found in the troposphere, aeroplanes often fly in its lower part. This gives a smoother flight with less turbulence. The textbook focus here is that the stratosphere is more stable than the weather-filled troposphere. Stratosphere: the ozone layer. The stratosphere contains a concentration of ozone gas known as the ozone layer. Ozone is a special form of oxygen with 3 atoms in each molecule. This layer is one of the most important protective features of the whole atmosphere. Ozone layer: filtering UV radiation. The ozone layer absorbs much of the sun's harmful ultraviolet UV radiation before it reaches the ground. This protection is important because excessive UV radiation can harm living organisms. In textbook terms, the key point is simple: ozone shields life on Earth from harmful solar radiation. Stratopause: boundary. The stratopause is the boundary zone marking the top of the stratosphere and the start of the mesosphere. At this level, the warming caused by ozone stops. It separates the calm ozone layer below from the cold layer above. Mesosphere: introduction and extent. The mesosphere is the third layer, reaching from about 50 kilometers up to around 80 kilometers. It sits above the stratosphere and is the coldest region of the atmosphere. The air here is extremely thin. Mesosphere: temperature behaviors. In the mesosphere, temperature once again decreases as altitude increases, dropping to the lowest values found anywhere in the atmosphere, well below freezing. This happens because there is no ozone here to absorb the sun's heat and very little air to hold warmth. It is the second layer, after the troposphere, where temperature falls with height. Mesosphere: meteorites burn up. Most meteoroids that plunge towards Earth burn up in the mesosphere due to friction with its air, appearing as bright streaks we call shooting stars. Even though the air is thin, there is enough to create intense heat by friction at their tremendous speeds. This layer therefore acts as a natural shield against space debris. Don't miss out where temperature falls. A key exam point: temperature decreases with altitude in only 2 layers, the troposphere and the mesosphere. In the other layers, stratosphere and thermosphere, temperature actually rises with height. Remembering this pattern of down, up, helps you avoid a very common mistake. Thermosphere: introduction and extent. The thermosphere lies above the mesosphere, stretching from about 80 kilometers to 700 kilometers. It is a very thick layer where the air is extremely thin. Despite its thinness, it has remarkable properties. Thermosphere, rapid temperature rise. In the thermosphere, temperature rises very rapidly with height because the few gas molecules present absorb high-energy X-rays and shortwave ultraviolet radiation from the sun. Temperatures can reach thousands of degrees, yet it would not feel hot because the air is far too thin to transfer much heat. This shows that temperature and heat we can feel are not the same thing. Thermosphere, radio transmission and ionosphere. The lower part of the thermosphere contains the ionosphere, a region of electrically charged particles, ions. This layer reflects radio waves back to Earth, making long-distance radio communication possible. Without it, radio signals would simply travel off into space.
Thermosphere, auroras. The spectacular natural light displays called auroras occur in the thermosphere. These glowing curtains of color appear mainly near the polar regions. They are one of the most beautiful natural phenomena on Earth. Aurora, meaning and origin. The word aurora comes from Latin and means dawn. It is named after Aurora, the Roman goddess of the dawn, because the shimmering lights reminded people of the colors of daybreak. The name captures the glowing, dawn-like beauty of the display. Aurora, solar wind and magnetic poles. Auroras form when charged particles streaming from the sun, the solar wind, are guided by Earth's magnetic field towards the magnetic poles. There, they collide with gas molecules in the thermosphere, making the gases glow in colors like green, red, and purple. This is why auroras are seen mostly in high-latitude regions near the poles. Aurora borealis and aurora australis. Auroras in the northern hemisphere are called the aurora borealis, northern lights, while those in the southern hemisphere are called the aurora australis, southern lights. They occur at the same time because both poles receive charged particles together. The two are mirror images of the same phenomenon at opposite ends of the Earth. Exosphere, the uppermost layer. The exosphere is the outermost layer of the atmosphere, beginning above the thermosphere and gradually fading into outer space. Its most striking feature is that the air here is extremely thin. Molecules are so far apart they rarely collide. It marks the true edge of Earth's atmosphere. Exosphere, escaping light gases. In the exosphere, gravity's pull is so weak that the lightest gases, mainly helium and hydrogen, can gradually drift off into space. Because the molecules are so widely spaced and moving fast, some escape Earth entirely. This slow leaking of light gases happens only from this outermost layer. Role of all layers in weather and climate. Each layer contributes to making Earth livable. The troposphere gives us weather and breathable air. The stratosphere's ozone shields us from UV. The mesosphere burns up meteors. And the thermosphere enables radio communication and hosts auroras. Together, they form one connected protective system. Weather and climate are the result of these layers working with the sun's energy. Don't miss out. Pressure on our bodies. A huge weight of air presses on our bodies at all times, yet we do not feel crushed. This is because the fluids and air inside our bodies push outward with an equal and opposite pressure, balancing the atmosphere's push. This balance is why we live comfortably under the ocean of air above us. The atmosphere gives us the air we breathe. It also acts like a shield, protecting living things from harmful rays coming from the sun.
Class 9 and 10 students, don't worry, make science and social science easy with your CBSE teacher. Subscribe now, like, comment, and press the bell.